Hello everyone, today we're going to learn about dissociation reactions and solubility. Now the main idea behind dissociation reactions is if we took an ionic compound, like the ones down here, and broke them up into their ionic components, what would it look like? Let's start with this guy, Ca3PO42. Ca3PO42. Now in order to break it up into its ionic components, we need to know what charge each ion would have. Out in front, we have the cation, which is calcium, and out here we have our anion. And in order to figure out the charges, you need to look at your handy-dandy periodic table. Now there's a nice trend that goes along here. With each column or group, you're going to have +1, +2, +3. We skip over carbon and those that go with it. Then we have -3, -2, and -1. First thing you're going to do is look for the stuff that you know you have. Calcium, that's on the periodic table. Let's take a look at it. It is number 20. And the more you look at the periodic table, the easier it's going to be to find these elements. We know that each calcium has a +2 charge, so I like to write +2 above it as a reminder. PO4, that's not on the periodic table of elements. That is a covalent compound, so it's made of a couple different ones. If you don't know it off the top of your head, we have a way to figure it out. Now this one down here is written as being neutral. So all the charges add up to 0. It has no charge. So we have to have the same amount of negative charge to counteract the positive charge from the calcium. Here we have 3 calciums, each with a +2 charge, and 3 times 2 is 6. We have 2 PO4s. We don't know what charge they have, so we're just going to call that X. And when we add both of those together, we should get an overall charge of 0. And now we solve for x. We're going to subtract 6 from both sides, giving us 2x equals 6. Divide by 2 to get x alone. You get -6. Got the negative sign. Divide both sides by 2, you get x equals -3. Now check to see if that's reasonable. +2 times 3 gives you 6. -3 times 2 gives you -6. Add those together, you get 0. Our answer seems good. Let's take a second to erase this. Now when you break these up into the components, you have to keep an eye on the subscripts. Here it's telling us we have 3 calciums. So when this dissociate some water, you're going to have 3 Ca plus 2s. A common mistake is to write it as Ca subscript 3 plus 2. This answer doesn't make any sense. That's telling me you have 3 positive calciums all stuck together with a +2 charge. To my knowledge, that is not possible. So remember to move the subscript out in front. Now for PO4. The subscript you care about is outside the brackets in the bottom right corner. And that is the one that's going to move out front. The PO4 is a phosphorus with 4 oxygens connected to it, covalently bonded. That stays together. It cannot be broken apart in this case. So subscript moves out front, so you get 2 PO4, and the charge that goes by it in the upper right corner is going to be -3. So this is what it would look like if it was broken up into its ionic components. Now let's look at the question of solubility. Would this actually happen? Now the rule for solubility is if you multiply the charges and it's greater than or equal to 4, it will not dissolve. Will not dissolve. Let's look at the charges. 2 times 3 equals 6. 6 is greater than or equal to 4, so this would not dissolve. And when you're doing this, ignore the positive signs and the negative signs. Just multiply the numbers together. You'll be fine. Now, I'd like to give you a little heads up now for when you take the second part of general chemistry, is there's a bit more nuance to this than it simply won't dissolve. So don't be surprised in the future when we come back to it and we learn a little bit more about the process. And you don't need to know that for Gen Chem 111. That's for the second part of the course. Now let's take a look at the next problem. K2CO3. What I want you to do is to break it up into its components, right, at dissociation reactions, and figure out whether or not that this is likely to dissolve. So pause the video, give it a go, then we'll check to see how you did. Okay, you've paused the video, hopefully you've given it a go, and let's see how we solve this problem. Here we have K, which is potassium. If you look over at the periodic table, this guy has a +1 charge. So +1. CO3, which is carbonate, is not on the table. So if you didn't know the charge off the top of your head, you could say, okay, we have 2 +1s plus x, our unknown, equals an overall charge of 0. Subtract 2 from both sides, x equals -2, so this ought to have a charge of -2. +2 minus -2 equals 0. That seems like a reasonable answer. Now if we break this up, we would have 2 potassium plus 1 plus CO3 minus 2. 1 times 2 is 2, and that is smaller than 4, so this is likely to dissolve. So now that we know that, we can actually add in physical states. If it has a charge smaller than 4, it's likely to dissolve. So we can call that aqueous. So it will dissolve. Aqueous, aqueous. A good rule of thumb is if it has a charge, it will dissolve in water. And if we go back to our first problem, this had a charge of +2, -3, making it insoluble. So we could actually have a little subscript of solid here. And these would be aqueous and aqueous. So let's take a look at question number 4. Which of these ionic compounds are expected to be soluble in water? Let's take a second and erase this. Let's start with NH4Cl. Will this dissolve? If you don't know the charge of NH4 off the top of your head, look at Cl. If you look over here, it has a charge of -1. And this overall has a charge of 0, so we know we need a +1 to counter it. 1 times 1 is 1, which is smaller than or equal to 4. So this will dissolve. This one's good. Let's take a look at BaBr2. BaBr2. Take a look over at our periodic table. Barium, number 56, has a +2 charge. Br, number 35 over here, has a -1 charge. 2 times 1 is 2, and that's smaller than 4. So this is going to be aqueous. So this one will dissolve. Now this guy has an interesting component that I want to talk about. CaNO3 2. Now NO3, this guy right here, has -1 charge, and this will always dissolve. Always. Big always. Even if it's paired with an exception like silver or lead, this will dissolve. Nitrates always dissolve. That is a big thing to learn. So that said, you wouldn't even have to look at the charges here. You could just see that it had nitrates on it. So yes, this would dissolve. Now AgCl. I just mentioned that silver can be an exception. Now if you didn't know it was an exception and you just looked at it, you'd think, okay, Cl has a charge of -1. That means silver should have a charge of +1. This should dissolve, okie dokie. But in real life, that doesn't quite work out. Here, silver does not dissolve unless it's paired with NO3. NO3 takes priority. If you get silver or something like PbCl2, lead, silver are exceptions that do not dissolve. They don't play nice. They don't dissolve unless they're paired with this guy. Now a common mistake that people make is dealing with nitrates is mixing it up with nitrites. NO3 minus is nitrate and NO2 minus is nitrite. How can you tell the difference? Think about the name. Nitrite has 2 oxygens and nitrite has 2 I's, 1 oxygen for each I. If you know that's nitrite, then the other thing must be nitrate. And that's where I'm going to end it here today with dissociation, reactions, and solubility. Keep on working at it. Good luck, and I'll see you in class.